All right, so I'm in the 8th slide now. So we have four kinds of quantum number. One is principal quantum number, Principal, principal quantum number. Qn is a quantum number, principal quantum number. So it is given by n, principal quantum number. It is given by n, and the value of n can be 1, 2, 3, 4, and infinite. Many values it can have. It is like this. So this is the neutron proton here at the center. So this is the n is equals to 1 first orbit. This can be second. This is second orbit. This is third orbit. This is fourth orbit, and you can draw as many orbits as you like. So what is the maximum number of the principal quantum here? Infinite, maybe 10, 12, right? So you can just keep adding those circle around the nucleus. So this gives the this is the principal quantum number, and its value can be from 1 to infinity. So principal quantum number cannot be zero. Cannot be zero. So there is no zero orbit here. Yeah. So it's like that. Now, how about the what does it give? So it basically gives how far is the electron is from the nucleus. So let's say, so this is the neutron proton here at the nucleus. So if the electron has n is equal to 1 value, where is the electron? It is right here. So how far is the electron from the center? It gives that. Make sense? And then it gives the how far is the electron from the center, number one, and another one is it gives the energy. So if you calculate the energy of this one, we calculate by RHC by n square. So this is constant, this is constant, this is constant, and if you put the value of n here, n is equals to 1, you can get the energy of the electron. So what does the principal quantum number give us? What is the information we can get from the principal quantum number? I am in the slide number 8, the last file, slide number 8. Yeah. So what is the principal quantum? What are the values of principal quantum number? It starts from 1 to and goes up to infinity. Yeah. There is no value of zero value for the principal quantum number. And what does the principal quantum number give? It gives the energy of the electron. So by using this equation, this is constant, this is constant, this is constant. So if you put the value of n here, you can get the energy. And we don't study in this class how far is the electron, so the radius from here to here. So that also can be obtained by the principal quantum number. So how far is the electron from the center, and what is the energy of the electron? So that can be obtained by the principal quantum number. Yeah, good. So how about the values of the azimuthal quantum number? Now, the second kind of quantum number is azimuthal quantam number. Azimuthal quantum number. Azimuthal quantum number, and it is given by L. So principal quantum number was given by N. Azimuthal quantum number are given by L. So they are the primary cell, they are the soft cell, meaning that let's say you are the here is a neutron proton, so n is equals to 1. So this is the principal cell. How many parts this cell can be cut into? That is called the soft cell, right? So cut this into how many parts? So n equals to 1. This cannot be cut. So this is given by this number. So this is minus. Sorry. So this is n minus 1. So the value of azimuthal quantum number is n minus 1. So I will show you what that n minus 1 is. So let's say if you have the value of n, so if you have the value of n, the L is, if this is 1, 1 minus 1 would be 0, right? Yeah, so the value of L would be 0, like this. Make sense? Good. Now, if the value of n is equals to 2, the value of L would be n minus 1. So 2 minus 1 would be like this, 0 and 1. So like that. Make sense? So always azimuthal quantum number, we always start from 0. Principal quantum number, we always start from 1, right? azimuthal quantum number, we always start from 0. So 0. So 0, and we cannot go up to 1. We should go up to 1 less than this one. Yeah, so it's a 1 less than 1. So this is if n principal quantum number n equals to 0, L is equals to 0 and 1. We cannot go up to 3. Make sense? So this number is 2, so we cannot go up to 2 here. So we cannot have 2 here. It's not allowed. Only 0 and 1. So let's talk about n is equals to 3. So I go here, and for n is equals to 3, what is the value of L? So L is the azimuthal quantum number would be, we cannot go up, we always start from 0, but we cannot go up to 3. Yeah? So we should just do like 0, 1, and 2. We cannot go up to 3. So 1 less. Yeah? So how many values here? If n equals to 3, 1, 2, 3 values here. And what is the last number value? So 1 less than, if this is a 3, this is the last number is 2. One is smaller than that. So they write the same thing by different way in these equations, but basically, once you know this one, you know everything. So when n equals to 3, L must be, it should start from 0, and it should not reach to 3. Yeah? 0, 1, 2. It cannot reach up to 3. Now let's talk about the n is equals to 4. So how about n is equals to 4? Let's say we have n equals to 4. So L should be starting from the 0, right? 0. So and it cannot reach up to 4. So L equals to 0, 1, 2, 3. It cannot reach up to 4. Yeah? Now how about n is equals to 5? If I have n is equals to 5, let's say here n is equals to 5. So let's say n is equals to 5. How about the value? What are the values of L? You should start writing from 0, right? And you cannot reach up to 5. So 0, 1, 2, 3, 4. So these are the values of azimuthal quantum number. Make sense? So like this. Now, if you have a 6 here, let's say if you have n is equal to 6. So what are the values of azimuthal quantum number? With the principal quantum number 6, azimuthal quantum number would be 0, 1, 2, 3, 4, 5. Can it be 6? No, it cannot be 6. It is 1 less than the principal quantum number. Yeah? Make sense? Good. Now, how about the, what does this mean? So what is 0, 1, 2, 3, 4 means? It is the, it gives the shape. What is saying here is a, let's say here, so the azimuthal quantum number defines the shape of the orbital. So I told you, this gives the energy, the principal quantum number gives the energy and how far is the electron from the center, right? So what does this tell us about? So 0 is spherical. So if you remember the last class, so what does the azimuthal quantum number tell us? So 0 means star, so the orbital is like this, S. So this is S. Make sense? So what does the 1 tell us? So I am just giving the shape here. So S is like the sphere or the soccer ball. Yeah? What does 1, what is the name of 1? We give name to 1 as a P. So this 1 is named as P. So what does that mean? What is the shape of that orbital? So I think this is a German word, P font. They call P FUND, P font. So that is like this dumbbell. So if this is 1, we immediately say that, okay, that's the shape of that orbital is like dumbbell, like this. 1, yeah? So it gives the shape of the orbital. So if you have a 0 azimuthal quantum number, the shape of the orbital is sphere. If you have the azimuthal quantum number L equals to 1, it can be like this. This can be like this, or this can be like this. So basically, the azimuthal quantum number 1 is saying that it is a dumbbell. So this is also dumbbell shape, this is also dumbbell shape, this is also dumbbell shape. So this is basically saying what is the shape of the orbital. Make sense? So the 2, if you have a 2 here, we give them name D. If 3 here, for 3, we give name F. If 4 here, we give name Z. So I don't know how the Z orbital look like. The F orbital also look like very complicated. We can go up to D. Yeah. So D is like the double dumbbell. So what is the shape of the this L is equals to 2? So that if you have the azimuthal quantum number 2, what would be the shape of the orbital? So it's a double dumbbell. Double D means double dumbbell. So if you have like this, so maybe this is one dumbbell like this, and this is another dumbbell like this. So 2 dumbbells are attaching each other. Make sense? So it gives the shape of the orbital. Yeah. So what does the azimuthal quantum number tells about? It tells about the shape of the orbital. Good. So there are 5 types of d orbital. So I'm not going to write here. So here we have one. I think we have up to z orbital. So let's stop here. Now let's talk about the magnetic quantum number. So it gives the shape of the orbital. So azimuthal quantum number tells us what is the shape of the orbital. If it is 0, it's spherical. If it is a 1, it's like a dumbbell. If it's a 2, it's a kind of the double dumbbell. Yeah. So I don't know what 3 or 4 looks like. Yeah. Good. Now, how about the fourth quantum number? Now let's say n is equals to, we did 3, and L is equals to, we did 0, 1, 2, right? So principal quantum number, azimuthal quantum number, we know how to write them, right? Now let's talk about the magnetic quantum number ML. So we call magnetic quantum number ML. So ML is should be derived from here. This one, and this one. So if L is equals to 0, so let's talk about the if L is equals to 0. If L is equals to 0, what is the value of ML, the azimuthal quantum number? Sorry, this is the magnetic quantum number. So this one is ML is magnetic quantum number. Magnetic quantum number. So we already do the azimuthal quantum number. From azimuthal quantum number, we derive the magnetic quantum number. So it's like this. So it is minus L to plus L value. Plus L value. Minus L to plus L value. So L is equals to 0. What is minus L? 0. Minus 0, right? What is plus L? 0. Plus 0, right? So plus 0 minus 0 or 0 is the same thing. So magnetic quantum number here is only 0. Yeah? So only 0. So if you have L equals to 0, magnetic quantum number is L equals ML is 0. Now, if L is equals to 1, if azimuthal quantum number L is equals to 1, so what is the value of ML? ML. So it's a minus L to plus L. So this is the L is equals to 1, right? So write the minus 1, 0, plus 1, like this. 3 values. Make sense? So let's say if L is equals to 2. So if L is equals to 2, if L is equals to 2, what is the value of ML? ML. So ML would be minus 2, minus 2, minus 1, 0, plus 1, and plus 2, like this. 1, 2, 3, 4, 5. Make sense? So we do like this. Now, what does this tell about? So what is the significance of the magnetic quantum number? I told you, principal quantum number gives the how far is the electron, or what is the energy of the electron. Azimuthal quantum number tells about what is the shape of the orbital, dumbbell or double dumbbell or spherical, right? And what does this tell about? What does the magnetic number tell us? It tells us like this. Magnetic quantum number just tells us like that. So how that double dumbbell is oriented, or the dumbbell is oriented. So let's say you have the so let's say L equals to 0, then you will have ML is equals to 0. So what is the orientation? What does this ML equal to 0 orbital look like? So this is a spherical. Spherical. ML0 means the orbital is spherical. Yeah. So it cannot, the azimuthal quantum number L equals to 0 cannot be divided further into smaller parts. So that looks to be spherical. How about the ML is equals to, let's say, minus 1, 0, plus 1. So let's say we have this quantum number, right? Ml is equals to -1, 0, +1. So it is coming from L equals to 2. So L equals to L equals to 1. L is equals to 1. So -1, 0, 1, right? So what is L equals to 1? So L equals to 0 is S. L is equals to 1 is P. L is equals to 2 is T, right? So this is the p orbital. So we are talking about the p orbital. So what is the shape of this orbital? What is the shape of this L is equals to 1 orbital? That is dumbbell, right? So P, dumbbell, right? So this is also dumbbell, this is also dumbbell, this is also dumbbell. So this looks like that. So this -1 may look like that. So the 0 may look like that. The +1 may look like that. So this is, I don't know which one is which. We cannot know which one is which. But this is a let's say this is a PY, this is a PX, this is a PZ. So these are the orientation. Yeah. So from the L equals to 1, what do we know? We know that this is also dumbbell, this is also dumbbell, this is also dumbbell. From ML is equals to -1, 0, and 1, what do we know? Oh, this one is oriented toward the perpendicular like this along the PY axis. Another dumbbell is oriented toward the x-axis, and another is oriented toward the z-axis. Like this is a z-axis. X, Y, and this z-axis. So, make sense? So this is the dumbbell. So 1, 2, 3. So p orbital are of 3 kinds. So L is equals to 1 at 3 kinds. 1, 2, 3 kinds, right? So they are dumbbell. Now ML values are 3. 1, 2, 3. This is 1. This is another. This is another. So what is this number telling us? Oh, one is oriented toward the y-axis. Another is oriented is toward the x-axis, and then another is oriented along the z-axis. Okay? So it is just to tell us about the orientation of those orbitals. Yeah? So we are done with the magnetic quantum number. Now, the last quantum number we have is spin quantum number. Let's say the last quantum number we have is spin quantum number, and it is given by ms. So what is the value of the ms? It's either +half or the ms value either -half. So ms can be +half or -half. It cannot be 0, it cannot be 1, it cannot be 1.5. ms values are always +half and -half. Make sense? Good. So like that. So what does this tell about? So I am telling that principal quantum number told us about how far is the electron, what is the energy of the electron, right? And the azimuthal quantum number say what is the shape of the orbital? Is it dumbbell? It is a spherical, or it is a double dumbbell, right? And then magnetic quantum number told us where is those dumbbell oriented. One is oriented toward the x-axis, another was oriented toward the y-axis, and another was oriented toward the z-axis, right? So that's magnetic quantum number. Now, what does this spin quantum number tell? So we have an electron here. This is the electron. Now we are not talking about the orbital. We are talking about the electron here. So this is the electron. So this is the electron. So the electron either rotating toward the anti-clockwise direction, or the electron is rotating in the axis toward the clockwise direction. So if it is rotating toward the clockwise direction, you can say +half. ms is +half. If it is rotating anti-clockwise direction, it is you say, okay, this is the spin quantum number is -half. So spin meaning that it is just rotating like this. So it's not like the rotating like this. It's just rotating. So this is the electron. So it is just here, and it is, if you rotate like this, this is a clockwise. Okay? So it's a clockwise. So I'm just rotating this like this. Yeah. This is a clockwise rotation. I'm just screwing toward my right hand. This is a +half. This is the electron. Now, if the electron is rotating like this, this is the anti-clockwise. Make sense? So I'm not talking about the electron revolving around the nucleus. I'm just talking about it itself is just spinning, like a spinning top. Yeah, like this. So this is a plus half. So this is a plus. If it is rotating like this, it's a plus half. If it is rotating like this is a minus half. Make sense? Good. So we have 4 quantum numbers. So like that one, and now we are done with this one. So so let's practice couple of problems here. Which of the following set of the quantum number of electron in a hydrogen atom? So I'm in the slide number 9. So which of the following is valid set of quantum numbers for the electron in hydrogen atom? So let's look number A. So question number 1 in A. So let's see, n is equals to, so A is like this, n is equals to 1, L is equals to 0, and ML is equals to 0, and then we have MS is equals to 1. I told you MS, can MS be 1, 0, or 2? It cannot be. MS always is either plus half or minus half, right? So this is clearly wrong. So if you see here, so maybe these things, I don't go to look here up to now, I just look this one. So this is MS is equal to 1. That cannot be happen. That is not possible. MS can either have a plus half value or minus half value, right? But it is saying that, oh, I have my MS equals to 1. So clearly, if this is wrong, everything is wrong. So this is not possible. So if one thing is wrong, all thing is wrong. Yeah? So A is not possible. Now let's look the B. N equals to 1. Because MS cannot have one value, either plus half or minus half. Now let's look at B. N is equals to 1, L is equals to 1, ML is equals to 0, MS is equals to minus half. This is good. MS value is good, right? This one is good. MS can be plus half or minus half, and it gives minus half. It's good. Now let's go here. L is equals to what? N. L is equals to 1. So if L is equals to 1, ML can be, if L is equals to 1, ML can be minus 1, 0, and plus 1, right? Yeah? That's what we told, right? CC, ML equals to 0. So that is one value from there. So this is good. Make sense? So to write this number, where did I look? I look here. L equals to 1. And then ML values are derived from L equals to 1. So L is equals to 1 is S, this is P, so this is PX, this is PY, this is PZ, right? Make sense? So this is good. So this number is good. Now let's go here and look P equals to L equals to 1. Now this number is coming from here, right? N equals to 1. So if N is equals to 1, L should be starting from 0, right? And it cannot go up to 1. That's what I told you, right? So is it possible if N is equals to 1, can L is equals to 1? No, it cannot be L equals to 1. L can only go up to 0. You see that? If N equals to 1, you start writing the azimuthal quantum number is 0, 1, 2, 3, 4. But this number cannot go up to the N equals this value, right? So it is wrong. Clearly wrong. So if one thing is wrong, all things is wrong. So B is wrong. Make sense? Good. Now, so don't look here. This is the father. This is the grandfather. This cannot be wrong. Yeah, it's just like the God people, right? So this cannot be wrong. So you don't look here. So look here, you look here, you look here, and one is wrong. Make sense? Good. So let's look at C. Where is that one? A, B, C. I have C. So C. So now N is equals to 1, L is equals to N equals to 1, L equals to 0, ML is equals to where is that one? C. ML equals to 1, and then MS is equals to plus half. ms is equals to plus half. First of all, we need to look here. Is it good? Yes, it is good, because ms has either plus half value or minus half value, right? So this is good. So now look, this ml is equals to 1. Where is it coming from? It should be coming from L equals to 0, right? So we are just moving back here. So if L equals to 0, ml value, we should start to write from this number, minus 0 plus 0, minus 0, 0 plus 0. So minus 0, 0 and plus 0 is the same thing. So I just write 0. But we can have only ml value is 0, but ml is 1 here. So this is clearly wrong. Make sense? So when it is wrong, we don't have to look other things. So this quantum number, the set of quantum number is wrong. Yeah, good. Now let's go to the D. D. So let's do D, and in D it says n equals to 1, L is equals to 0. ml is equals to 0 and ms is equals to minus half. So this is good. Ms is equal to minus half or plus half is good. So you don't have to look here. This is good. Now look, ml equals to 0. So this number is coming from here, right? The previous one. If it is 0, ml values can be 0, minus 0, this number, minus 0, 0, plus 0. So this means that minus 0, 0, plus 0 is the same thing. So we just write the 0. Is it good? ml equal to 0. This is good, right? Make sense? Now let's go here. L equals to 0 here. So this number is coming from here. So if n is equals to 1, L value start from 0 always. So it 0 and can it go to 1? It cannot go. When n equals to 1, the L value start from the 0 and it cannot list up to this number. Yeah? That's what we have been telling. So it cannot go up to 1. So I cannot write 1 here. So 1 is 0. So this is 0 here. So this is good. So you don't have to look now. So this everything is good now. Yeah? Good. So let's practice some other problem. So how many quantum number are possible in one orbit? So let's talk that thing in with slide number 10. In slide number 10, so let's say n is equals to 1. So how many quantum number are possible here? So you just give by this n square. So n is 1, 1 square would be 1. So if n is equals to 1, so if the principal quantum number is the first orbit, there is only one orbital possible, like this. So this is the first orbit. So n is equals to 1. How many houses you can cut the first house? N is equals to 1. You cannot cut into anything, right? So there is only one possible orbital, and we give that as a 1s. So this is 1s. So only one orbital is possible when n is equals to 1. Yeah. Now let's talk about n equals to 2. So how many orbitals are possible? N square. So it is given by n square. So n is 2. So 2 square is 4. So 4 orbitals are possible for n equals to 2. So if you want to write here, it's like this. So when you have n is equals to 2, so you have n equals to 2. Now you write the L equals to start from always 0, 0, 1, and never is 2, 2. Yeah? Cannot reach up to 2. Now write the ml value. So it's for 0. So for minus 0, 0 plus 0. So this is the same thing. Minus 0, 0 plus 0. So ml value for this one is only 0 for this one. Now this 0 is coming from this one. Now for this one we need to write the ml value. So for the ml value for this one is 0. For how much is this for this one? So ml would be for n equals to 1. For n is equals to 1, ml would be minus 1, 0, plus 1, like this. So from this one we come minus 1, 0, plus 1, like this. Yeah. Good. So now how many values we got here? 1, 2, 3, 4, 5, 6, 7. I should have so n equals to 2. We should have a 0 plus 1, 0 minus 1. Sorry. So we look here. So 1, so 2, 3, 4. So we have 4 values of quantum number here. Yeah. So this one is a ml equals to 0 is a s orbital, and this is this looks like spherical. Maybe this one looks like this. This one looks like this, and this looks like this. Yeah. So only 1, 2, 3, 4, 4 kind of the species exist when n equals to 2. Make sense? Good. So like that. Now, how many orbital are possible there if n is equals to 3? N is equals to 3. So that's a n square. 3 square will give you 9. Now, if you want to write those 9 orbital, so you can write like this. So let's say we have n is equals to 3 there. Then now you have to write the L equals to starting from 0, 0, 1, 2, and you cannot go up to 3. 0, 1, 2, and then now you have to get the ml values for 0. So ml values for 0 is 0. So ml values for 1 is minus 1, 0, and plus 1. And ml values for L equal to 2 is minus 2, minus 1, 0, plus 1, and plus 2. So how many? Can you count here? How many spaces are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 kind of species exist there for n equals to 3. Make sense? So if you go to the n equals to 4, 16 type of species exist around that orbit. So ml, what is the shape of this one? What kind of the shape this here? It's just like a spherical. And then what kind of this one? It's coming from 1. So one look like this, another look like this. This may look like this orientation. So this is orienting y-axis. This is orienting toward x-axis. This is orienting toward z-axis. So these 3 are this one. Now this is the D. So this is S, spherical. This is P, like dumbbell. This is D. This is a double dumbbell. So this looks like a little complicated. So those spaces look like this. Those D are white. So these spaces, minus 2, minus 1, 0, plus 1, plus 2 spaces look like this. So one look like so. You see, this one look like that. That is space. Yeah, and then this one look like this. So these lobes are directly pointing toward the x-axis. Yeah, here the lobes were between the axis. Here these lobes are pointing directly toward the axis. And there is another looks like this space. So this looks like this, and there is a tiny space here like this. So another look like this. So 1, 2, 3. I draw 3. Now there are 2 other there. So either 3 dimension. It's a little bit hard to look. So those 4 look. This 1, 2, 3, 4, 5 looks like something like this. Yeah. So I draw 3, and then you can draw other 2 more, just like this one and this one. But the axis will be a little bit different. You can just Google this and look. Oh, what is the shape of the orbital? So shape of the D orbital. So this number for the D. So this minus 2, 1, 0, plus 1, plus 2. They are coming from L equals to 2. And this is also double dumbbell. 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 Make sense? Good. Okay. Now, alright. So we are done with the slide number 10. Now, basically slide number 11 and slide number 12 is saying the same thing what I talked now, so you can read yourself. Now let's do some problem in slide number 13. So this is important. in homework, I put in exam. Yeah, so quantum number are important in physics, chemistry, engineering when we do this kind of thing. So I never understood when I was a student. I only started to understand when I started to teach. Yeah, so this is a little bit confusing. Now, I'm in the slide number 13. What level is given to an orbital with a quantum number n is equals to 4 and L is equals to 1, like this. Yeah? So what is the name of this one? So I told you, so n is equals to 4 doesn't have a name, so it has a name. So if n is equals to 0, 1, 2, 3, like this, so for this one, we give now name S. For this one, we give P. For this 2, we give D. And for 3, we give F. Like this. Okay? So the azimuthal quantum number 0 is named as S, 1 is P, 2 is D, 3 is F. So what is the name of this one? So N is a 4, and it has a name S. So 1 is S. So this is 4s orbital. Make sense? 4s. So, oh, sorry, 0, 1. No, not 4s. Not 1 is P. You see here, 1 is P, not S. 1 is P, right? So this 1 is P. 4P. 4P. So if you have n equals to 4, L is equals to 1. Another way of saying the same thing is the orbital I'm talking is 4p. So this is in the 4th orbit, and the shape of that space is dumbbell, like this. Make sense? P means it is a dumbbell. Where is that space located? It's far from the nucleus in the 4th orbit, around near the 4th orbit. Yeah? Good? So like that. So what I'm talking, what does the 4p mean? What does the 4p mean? 4p means like this. So I'm talking about the electron, not in the first orbit, not in the second orbit, not in the third orbit, and only I'm talking in the electron in the 4th orbit. So I'm not talking about these 2 orbits here. I'm talking about the electron in the 4th orbit. Electron in the 4th orbit. Where is that electron? So that electron is in the like this kind of thing. So maybe there is some dumbbell space like this. So electron is that space, not in the spherical space, not in the spherical space, but it is in the dumbbell type of space that electron is inside. 4p. Make sense? So the electron is in the 4th orbit, and that 4th orbit is divided into many spaces. And what kind of spaces that electron is? It is in the p type, meaning that the electron is in the dumbbell type of space, jumping in that dumbbell type of space. Yeah. So we'll talk more in the 7th chapter, and you will know more. Yeah. So now, how many orbitals is equals to n equals to 4? So how many orbitals in n equals to 4 in the second question? So to calculate the number of orbitals, you do n square. So n is 4 square. So that is 16. In n equals to 4, there are 16 type of spaces. So if you are talking about the 4th orbit in the atom, so that 4th orbit can be divided into 16 type of spaces. Yeah. So some are spherical, some are dumbbell, some are double dumbbell. Yeah. Make sense? So the 16 type of spaces are there. Now, how about which quantum number or the combination of quantum number is needed to specify given subcell in the atom? Subcell means, so this is a cell. The first is called cell or orbit. The second is called subcell. The shape of the orbital. So L is equals to, if n equals to 4, L can be 0, 1, 2, 3. So we just need 2 things. Yeah? So the question was, which quantum number or combination of quantum numbers is needed to specify given subcell in an atom? So we are talking about the subcell. So where is the subcell? In the 4th orbit. We are not talking about the subcell of 3 or 2 or 1, right? And then what kind of the subcell exists there? One looks like the spherical subcell, another looks like the this kind of space. This L equals to 0 looks like this kind of space, this looks like this kind of the space, and this also looks like the dumbbell type of the space, and this is also look like the dumbbell. That's very like this space. Yeah, make sense? So this is the kind of the dumbbell space. So if you are talking about the n equals to 4 and 0, you are talking about, oh, I'm in the fourth orbit, and I'm just talking about the spherical space in that fourth orbit. If you are talking about the fourth orbit and L equals to 1, you are talking, oh, I'm in the fourth orbit, and in that fourth orbit, there is a dumbbell shape. I'm just talking one kind of the dumbbell shape, right? Good? Yeah. Good. Now, let's look in review it. All right. So, which of the following is not correct representation in an orbital? So, it's a number 1 in the slide number 13. If you check for section 6.6, so number 1. So, let's see that one. So, is 3s possible or not? So, let's look at 3s. Is it possible or not? So, 3s orbital we are talking. So now let's break into quantum number. N is equals to, so this number is 3. The first number there is 3. So we are talking about the electron that is in the orbit 3. And what is the value of L for N is equals to 3? So it is, you should start writing from 0, right? 0, 1, 2. You should not reach up to 3. 1 is 0, 1, 2. Yeah, 1 is then that number. Now, what is the value of this S? What is the name of S? We give S. What is the name of this one? We give number P, the letter P. For this 2, we give letter T. So is there a 3? Yes. Is there a S? Yes. So this is good. This is not wrong. This is right. Yeah. So how about the 3P? Is 3P good or bad? Let's look at the 3P. Is there a 3? Yes, there is a 3. Is there a P? Yes, there is a P. So this 3P is good. Yeah? Okay. So now, how about 3D? Let's look 3D. 3D. Is 3D good or not? We have 3? Yes, we have 3. Good. Do we have D? Yes, we have D here. So this is good. So first we make the set of the quantum number and look whether those numbers are there or not. Yeah? 3S, 3P, 3D are good. How about 3F? Now let's talk about the 3F. So the last one is 3F I have, right? 3F. So S, P, D, F. Can I write 3 here? I cannot write 3 here because if n equals to 3, I should start from 0, 0, 1, 2, and I should not go to up to 3. Yeah? So that if I have wrote 3 here, I could give 3, and only 3F would exist, but it's not possible. So 3 is not there. So 3 is there. This is good, but F is not there. So this is 3F is bad. Yeah. So write all quantum number and write those later, and then should be good. Now, which of the following set of quantum number correctly represent 4p? So I'm in the question number 2. Let's talk about the 4p. Question number 2, 4p. So 4p, I have this one. So I need to write the quantum number for 4p now. What is the n value here? N value is 4. So the first value is always 4. That's a grandfather. This is big cell, 4th cell, right? And then other are his children. Now n equals to 4. Now what are the values of L now? So we should start from 0. 0, 1, 2, and 3. We should not go up to 4. 0, 1, 2, 3, right? And you give the name here S, give this name P, give this name D, give this name F. So now let's write the quantum number. So n is equals to, I have 4, n is equals to 4, good. Now n is equals to, you can write any name, anything, 0, 1, 2, 3. So we will write L is equals to 0, L is equals to 0. I'm just looking at the question number in 2A, so L equals to 0. This is good or not good? So n equals to 4, good. L equals to 0. We have L equals to 0. This is good. And then I have ml is equals to -1 here. Ml equals to -1. Can it be -1 here? No, right? Because if L equals to 0, it can only have the -0, 0, plus 0, meaning that it is 0. But he's giving -1. So -1 cannot come from the 0. So this is the father, this is the children. From L equal to 0, father, ml equals to -1. That cannot come. Okay? So this is basically S, and this is P. This is kind of P. So this cannot, P cannot come from this. Make sense? P must be coming from the P. Yeah? So this is not possible. So this number cannot come from here. So A is bad. So let's look a good one. So good one here is B, and why it is good, I'm going to write here. So 4P, and let's look the number D here. So that is good one. So why it is good one? So in number D, they write no, in number A, B is good. N equals to 4, L is equals to -1, ML equals to 0. Is it good or not good for 4P? So N equals to 4, this is good, right? It's 4, right? And then now for 4, N equals to 4, L can be 0, 1, 2, 3. If you have N equals to 4, L should be writing from 0 and go up to 3, not up to 4, right? So this is S, this is P, this is D, this is F. So 4P. So do I have L equals to -1 here? Is it L equals to minus? I think it is L equals to 1, not -1. So I think it's a little bit mistake here when I was circling. So this L equals to 1, yeah? It's not L equals to -1. Do we have a 1 here? When N equals to 4, we have 1 here, like the P. So this is good, this is good, this is good. Or you can go from here also. So this is good. 1 and L equals to 1 is good. Now this one is a P. This one is a P. Now, if I write the L equals to 1 here, what are the values of ML? So I should start writing from -1, 0, and +1. You see that? So this is a L equals to 1. Just say, oh, it is a dumbbell, right? It is a dumbbell. But how many kind of dumbbell there are? There are 3 kind of dumbbell. One is orienting toward X. Another is orienting toward Y. Another is orienting toward Z, right? So this one. So this is P. So this is one may be PX. Other is PY. Another is PZ. So it's definitely one of those. This one. So from those P, maybe out of those 3 P's, one is this one, which is good. Make sense? So good. So this one is right. This is 4, N equals to 4, and then P means 1, and from if L is equals to 1, ML values can be -1, 0, and +1, and we have 0 here. So that set of quantum number is good. Yeah. So in the next class, I will finish this quantum number practice. So from number 3, and then we will start chapter 7 on Monday. Yeah. So it's the right time. So we have just 7, 8, 9. We have 3 chapters. So we are done with the most difficult parts. So 7, 8, 9 are pretty easy. Yeah. Good. Alrighty, thank you everyone. I'm going to stop this one.